Welcome again to this IF Oxford event where we're exploring the stellar cluster of fusion technologies across Oxfordshire. And I'm going to pass on to Valerie.
Hi, I'm Valerie Jamieson, and as Dane said, I work at UKAEA in Culham, and I manage a new fusion technology cluster. Quite what that is, we'll explore a bit later on in this webinar, but I'd like to introduce this session and our panelists. But first, fusion energy is the process that powers our sun, and we can use that same process to provide abundant, low carbon power for generations to come. And when it comes to fusion know-how and skills, there's no other place on the planet quite like Oxfordshire. Joining me to discuss why is our panel. And now we can introduce Lindsay Mooring, who manages the Fusion Industry Programme at the UK Atomic Energy Authority in Culham. Lindsay is one of my colleagues. Hello, Lindsay. We also have Gianluca Pisanello, who's the Chief Operating Officer at First Light Fusion in Yarnton.
Hi, everyone.
Gianluca, hi. Chris Grosvenor is Professor of Materials at the University of Oxford. And if you're wondering what materials have got to do with fusion, we will definitely be exploring that one. Hello, Chris, welcome.
Hello, everyone.
And Ross Morgan, who is Commercial Director of Tokamak Energy in Milton Park near Abingdon. Hello, Ross.
Hello, everyone.
Now, our discussion is going to be in three parts. First, we're going to talk about fusion, then we'll talk about Oxfordshire's special role when it comes to fusion, and finally, how you can get involved. Now, don't be shy, don't wait till the end to ask your questions. We'll be pausing at several moments throughout this event to take audience questions. So please, as Dane said, use that little Q&A box right at the bottom of your screen with a little speech bubble and ask your questions in there. So let's kick off. Now, Lindsay, for people who aren't so familiar with fusion, could you just give us a quick primer, please?
Sure. You've already mentioned that fusion energy is the process that powers the sun, in fact, all the stars, and they are the natural fusion reactors that we're aware of in the universe. And the way it works is fusion energy comes about by combining small light elements, atoms, in very extreme conditions. It's the opposite of the way nuclear fission plants work, where they split large, heavy atoms. And what we need to use is light fuels for that. So we typically use the heavy isotopes of deuterium and tritium, and we fuse those together, as I say, in extremely extreme conditions. Extremely extreme, and that releases helium and energy, and it's capturing that energy that occurs in that reaction that is what we are all working towards to try and put energy on the grid.
Now, Ross, the idea of fusion energy has been around for decades, and people have been doing experiments in fusion reactors for decades as well. Why is fusion not on the grid already? Why is it taking so long, and what are some of the challenges?
Well, it's actually very challenging and technically very difficult, as both yourself, Valerie, and Lindsay have alluded to. What we're trying to do here is recreate a process that occurs within the sun and the stars, but do that on Earth. And you know, this involves a whole range of scientific and engineering challenges. You know, we need to try and create temperatures that are, you know, hotter than the center of the sun and the stars, going up to 100 million degrees. And as I'm sure everyone can appreciate, you know, that isn't straightforward. The sun and the stars have the benefit of huge gravitational fields to, you know, to hold the fusion process in place. You know, we can't use that when we're trying to generate fusion on Earth. So one of the approaches is to use magnetic fields to contain the fusion reaction. And we're having to develop extremely high field, robust and reliable magnets to do this. And then, you know, thinking about what Chris and his team do, you know, materials, we're having to look at developing materials that can withstand these very harsh and challenging environments, and they need to last for the lifetime of a commercial fusion power plant, which can be many decades. And as you know, I'm sure everyone can appreciate that itself throws up a lot of challenges. But you know, I think one of the other elements is that you mentioned, Valerie, that about all the different experiments that have been going on in fusion, and I think there has been a change in the view. I think historically people have thought of fusion as, you know, an experimental program, but I think, you know, the current environmental and energy challenges we face have made people realize that actually we need to think differently about fusion and think about it in a commercial way. And I think, you know, we've seen in recent years a significant increase in the amount of public and private investment that is going into fusion. And I think that, you know, is going to enable us to move much faster towards our end goal, which is, you know, commercial fusion on the grid.
Now, you talked about the all the challenges that fusion faces. So I would like to bring in Gianluca now, because Gianluca, we've seen a remarkable growth in renewable energy over the past decade, particularly in wind power in the UK. If it's going to take us another 10 or 20 years to get fusion on the grid, you know, could renewable energy just catch up? Do we still need fusion?
Thank you. This is a very good question, and a question I think many or most people actually ask or wonder. I was one of them, to be honest. It is amazing. I mean, the deployment, the development and deployment of renewables is amazing, and we should absolutely insist and accelerate that deployment. In fact, but you know, we at First Light specifically, we wanted to answer that question because obviously there's a number of people at First Light, at Tokamak Energy, at UKAEA who are investing their lives and careers. Some of them have jumped careers to invest in their careers into this. So we commissioned 3 years ago an independent study to try and understand how the energy landscape would look in 2040. To make sure that we were not working for nothing, basically, because there would be no need for it. Now, the 2 important aspects to consider are that there is an enormous increase in energy demand in general due to growing population and due to rapid development of a lot of countries which are heavily populated as well. So that's one aspect. And the second aspect is obviously there's also a shift into electrification for great reasons, of course. So these two elements combined make so that the energy demand and electricity demand is going to increase exponentially in the next few years. And the result of that study is that basically what we asked this consultancy was to take a very aggressive approach, both in the cost reduction of renewables and also in the deployment speed of renewables. The outcome is that in 2040, basically at this aggressive deployment, even at this aggressive deployment, renewables would cover slightly or definitely less than half of the projected energy demand. So there is an obvious and very strong need for a different form of baseload energy. Please note that I haven't even touched on the potential aspects that some people bring up of renewables not being a continuous source of energy. It may very well be that combined with battery developments by 2040, that will be solved. What I'm saying is just that there isn't enough deployment capabilities, which is not even linked with how much money you can throw at it, to actually deploy enough renewables to cover even half of the projected demand. So fusion, obviously being clean and being a very, very safe source of energy, is a fantastic candidate to plug that gap, which otherwise can be plugged in either using sort of conventional nuclear, which for reasons which are not out of this panel has a relatively low, still a relatively low public acceptance, and also some practical deployment issues. Or that gap will have to be plugged by non-clean sources of energy.
Okay, so we've seen that fusion doesn't produce carbon dioxide in the reaction itself. It's safe in the sense that you don't get a runaway reaction. So this is all sounding great for fusion. Chris, you've been involved in fusion for many years, and an independent, you don't work for, UKAEA or any of such companies. You're probably the most independent of us all. How have you seen the landscape change over the past, 1 or 2 decades?
Well, it's dramatic. When I became interested in fusion materials, and if you're containing the sun in a small bottle, what you contain it in becomes quite important, and the materials, as Ross has said, become an extremely challenging part of the whole program of designing and building a reactor. When I started working in the area, there were 2 projects that we talked to, essentially. There was the NIF project in the States, the National Ignition Facility, and there was the ITER international program, 35 countries building a really huge fusion reactor down in France. And the idea of the small companies, the entry-level companies with maybe 50 to 100 people being able to design and build a reactor, we never imagined that was possible. So it was national funding, very large amounts of national, multinational funding to build huge prestige projects, many of them taking many decades. And what's come online now is the lean and mean, quick, come to market fast, small reactor. The technical problems are still fairly similar, but the engineering scale is much reduced, so that you can't exactly fit the reactors into this room, but the whole scale has come down a lot. And smaller companies with private investors rather than national investment have come to the fore. And Ross and Gianluca are representatives of exactly that new trend in and around the world. There are many others. There's a Canadian company relocating into Oxfordshire, bringing their different technology in, their different approach to fusion. So it's just a completely different landscape, all of which are going to require materials to make them work, I'm glad to say, because it keeps people like me in jobs.
It's going to keep you very busy, isn't it? But as you said, for me, what's really exciting is that there are lots and lots of different approaches to fusion. Some of them use lasers, some of them use some really sort of crazy sounding ideas. But Lindsay, at Culham where you work, the Joint European Torus, or JET, has been doing experiments since 1983, and it currently holds the world record for fusion power. What approach is taken in JET and at the other fusion reactor at Culham called Mast Upgrade?
Yeah, so we've touched on it a little bit as we've been talking through this, that the approach that we take is actually based on magnetic confinement. So I mentioned earlier around we have the heavy isotopes of hydrogen as our chosen fuels for our plasma reactions, for our reactions, but for them to work, we can't just have them in the gaseous state, we actually have them in a plasma. So a plasma is a superheated ionized gas, and because it's ionized, you can control it, shape it, work with it by using magnetic field to control it. So you have these electrons are stripped away from the atoms, it's charged, you can shape it with a magnet, it's at really high temperatures, you effectively have a magnetic bottle around it, and for it to be a continuous reaction, we put it into a ring shape, into a donut, and that's where we get the phrase, or the name for it being a tokamak, which is a Russian acronym for this approach that was come up with decades ago. And that's been the focus of research at UKAEA because of the history of what occurred then. But there are definitely other approaches to it. And there's an awful lot of overlaps that are useful for the whole of the fusion approaches that can be all of us to pull together and work towards for.
Now, Ross, so you're commercial director for Tokamak Energy, and as Chris said, you know, one of these lean, mean, fast, innovative private fusion companies that's in Oxfordshire. Tell us a bit more about the company's history and the approach that Tokamak Energy takes to fusion, because there's a lot of similarities with what Lindsay just said.
Absolutely, and I don't often get described as lean, mean and fast. I think my children would take issue with that. But no, that's right. I mean, Tokamak Energy was founded just over a decade ago, and our founders were actually physicists working at UKAEA at the time, and you know they felt that there was perhaps a better and a quicker way of addressing the fusion challenge than perhaps the mainstream government programs at that point. And they also felt that if being a private company, as Chris alluded to, it gave you the ability to be more agile, more flexible, and move more quickly. So as I say, our founders set up the company just over a decade ago. And the technology that they were promoting at the time was a variant of the donut-shaped tokamak that Lindsay referred to, called the spherical tokamak. And the spherical tokamak has, you know, a number of benefits over the conventional tokamak in terms of its efficiency and potentially the amount of power that you can generate for a given size. And they looked at combining this advanced spherical tokamak technology with the latest developments in high field superconducting magnets. As Lindsay again alluded to, you know, we're using magnetically confined fusion, so we need very powerful magnets to hold everything in place. And you know, at the time, there were a new generation of superconducting magnets coming through, which could generate and sustain higher magnetic fields than the more traditional superconducting magnets. And it's the combination of these two technologies that leads to a solution that is potentially more compact, but also more cost effective. And I think for us at Tokamak Energy, that is one of the drivers. We recognize that people are not going to deploy fusion as a source of power just because it's really great science and really great technology, which it is, by the way, but it's going to have to be economically and commercially competitive. And so we're looking at it from that perspective, and that really drives our development and our business model. It is all about delivering something that can be deployed commercially. So, you know, over the last 10 years, our company has grown quite substantially from 3 people when we started. We're now just around 180 people. You know, we've taken the approach of building and testing devices to prove out the technology that we're developing. And as Chris said, you know, we've been able to do this in a relatively short time frame. We've built 3 prototype devices or tokamaks over that time. We're currently operating our 3rd device, ST40, which we're using to demonstrate that we can achieve the conditions that are required for fusion.
And it's incredible that you've got all this going on in Milton Park. As I said, I get really excited about fusion because there are these different approaches. And John, look at First Light fusion, you are taking a completely different approach. So sort of same question as I asked Ross, you know, tell us a bit more about it and tell us a bit more about the company's history and how many people you employ now.
Yeah, sure. I'll take one step back before I introduce the technology. to sort of back to the fusion 101 Lindsay was talking about, to get, as Lindsay said, the state of matter we deal with when we deal with fusion is extreme. And she rightly mentioned the temperature, which has to exceed 100 million degrees. To get fusion, to get these isotopes of hydrogen to fuse, you need in fact three things broadly from a physics perspective. You need the temperature, which is basically is a measurement of how fast the particles go, and this is to force these particles to hit each other very, very hard. Then you need a certain density of these particles, because it doesn't matter how fast they are, if they don't find each other, it's going to be difficult that they fuse. So you need enough in a certain amount of space. And then you need time. You need enough time for a significant number of these interactions to occur. Now, temperature is pretty much a given of these three parameters. Is pretty much a given. You need 100 million degrees. Unless you want to start talking about cold fusion, but this is not something I'm going to comment on. And I think Chris doesn't want to comment on either. So temperature is a given. You need very, very high temperature. The other two parameters, which are density and time, are very much interchangeable. These three parameters together are so interlinked that sometimes they are referred to with a single name, which is called a triple product. Basically, there's a law which says that if a triple product is above a certain number, then your fusion works, basically. The parameters of density and temperature, as I said, they are very, very interchangeable. So you have magnetic fusion where you have a time which is very long. You can measure it in seconds or minutes, maybe in the future, or maybe longer. But the density is very, very low. The plasma in a tokamak is very rarefied, much more than the air in the rooms where we're in. Our approach, which is inertial confinement, is at the opposite end of the spectrum. It's still a mainstream approach. The most famous laboratory research in it is what Chris mentioned before. It's called NIF, National Ignition Facility in California, at the Lawrence Livermore Laboratories. The way we try to achieve fusion is to have the plasma confined by its own inertia. So what does it mean? The plasma has a certain mass, and therefore it cannot cool down instantaneously. It has a certain inertia before it relaxes. And what we try to do is, like NIF, we try to basically make the fusion reaction happen before the plasma has the time to relax. So our approach is much more, in a way, short. So our time component is very short. We talk about nanoseconds, so billionth of a second, but our densities are way higher by the same amount. They must be, because of the triple product. So in our case, when our plasma fuses, or when NIF plasma fuses, you can imagine that these hydrogen atoms are denser than lead, basically are denser than the center of the Earth. And then they are still 100 million degrees, but only for a very, very, very short time. Obviously, what happens is that you get a burst of neutrons. Instead of having a continuous sort of flow of neutrons, like in a tokamak, you get a burst of neutrons. And then what you do, you repeat this process. So it's sort of a pulse process. The way we sometimes describe to sort of get the difference with a chemical analogy is we say a tokamak is like a furnace. So basically you have this process that continues to burn, you keep injecting fuel, and that keeps burning. Inertial fusion is a bit more like an internal combustion engine. You inject the fuel, you spark it somehow. NIF does it with lasers, we do it with projectiles. And then you let the engine release the energy, and then you repeat the same process again. So this is what we do. Why do we bother to do this? Is because we believe it actually sidesteps a few of the major engineering challenges that there are in fusion reactors. Because obviously, as Ross said, we're not here just because the science is really cool, but we also need to deliver clean energy. So we have to think about the reactors. Our approach is based on projectile. Basically, we generate the conditions by hitting a target with a projectile, and that the shockwave, the resulting shockwave, compresses our gas in a similar way that the lasers do at NIF. The difference why we do it with projectile, first of all, is because it's much cheaper than doing it with lasers, and the energy delivery is much more efficient than doing it with lasers. But the additional advantage is that the projectile gives a degree of separation, of space separation, from where the sophisticated, delicate, expensive equipment is, and where the reaction actually happens, which, as you can imagine, is quite a brutal environment in terms of temperature, in terms of neutron radiation, and this, we think, offers some actually sidesteps what problems with heat flux, with neutron flux, and also we don't have the time to go into the details of that, but also in how we make tritium. Every fusion power plant will have to breed, technical term, or make, produce their own tritium by using the neutrons of the reaction combined with lithium somehow. Very shortly about the company. The company was founded in 2011, so exactly 10 years ago, in fact. We are currently 65 people and located in the north side, of just outside Oxford on the north, near Kidlington. This is what we do and who we are.
Yeah, amazing to think that's just all happening outside Kidlington there. And now you mentioned some materials there, and let's bring in some audience questions now. Peter Russell says, although the fusion fuel is plentiful, as Lindsay mentioned, Peter asks, are the specialist materials required to build the reactor vessel and the magnetic components going to be rare enough on Earth to create a new shortage? Chris, how would you respond to that question?
I've just been typing an answer into the box, but I'm happy to talk about it as well. I mean, building even a small power plant, almost all the materials will be conventional engineering alloys, the kind of things we build all sorts of other stuff out of. There's the sun in the bottle, and near that you're going to have to deal with a lot of heat dissipation. There's not many materials that can cope with that. It'll be something like tungsten. There are breeder, like Gianluca's saying, we've got to breed tritium, the fuel, that'll be in a lithium or lithium alloy. The battery people are going to fight the fusion people for the source, for the lithium. And so it will be interesting to watch that happen. But essentially, most of the materials will be conventional ones, but we already know from the designs of all the reactors, all the different technologies, those materials be running right at the top end of their capabilities. And that's the challenge, is that how are you going to design something that will work for 40 years, providing power to the grid for 40 years with materials that are close to their operational limits, right from day one to year 40. That's a genuine problem.
Mm-hmm. What I love about fusion is on paper it sounds completely bonkers. You're creating temperatures hotter than the core of the sun, and you're using you might be using superconducting magnets that are chilled to just above absolute zero, and this is all happening just within a few centimeters of each other, and it sounds bonkers, but knowing physicists and engineers the way that I do, they are blooming ingenious people, and they'll make this happen. We spent a lot of time we just had a question from from Phil, who asks, how will demo be started if ITER has used up the global supply of tritium? Chris, could you answer that? Because that's, again, talking about tritium, and you maybe want to mention, bringing the idea that we make tritium.
Tritium is a product of running certain kinds of conventional fission reactors. So if you have deuterium in your fission reactor, so a heavy water reactor, you get some tritium naturally. And so the CANDU reactor designs that are designed and run in Canada and some other countries, they do produce tritium. And if you want tritium, you can go and buy it. In fact, on the Culham site, UKAEA has a tritium processing facility. So that's not an impossible problem. The problem is that during a reactor running, tritium will have to be bred in the reactor, and actually nowhere in the world has ever quite demonstrated that technology, and so that's a big challenge for the whole community.
And while we've got you on a roll, Chris, William has just asked, given that it takes energy to keep the hydrogen hot enough and the magnets to work, is fusion going to take more energy than it produces?
I think my colleagues are the ones that should answer that. They're the engineers.
I can jump in on this one.
Yeah, briefly, if you could, John.
Yes,
we've got
absolutely.
a lot to get through.
And obviously, if that was true, we wouldn't be doing this. This is the quickest question, but obviously it is a very good question. At the moment, nobody has demonstrated they can generate more energy than the energy they require. ITER is the big, let's say, is the big public effort to do that. I think I can talk for Ross as well. Both Tokamak Energy and First Light Fusion think they will be able to get to that point, which is called sometimes net gain in fusion community. We think we should be able to get to that point quicker than that. So the answer is no to your question. We aim to generate more energy than we suck in.
Yeah, great. Thank you, Gianluca. So I said in my introduction that there's nowhere else on the planet with such a high concentration of fusion activity. Chris, briefly, how did Oxfordshire just become such a focus for fusion?
Well, a lot of these things are sort of by accident. I mean, 50 years ago, no one said, let's make Oxfordshire the fusion capital of the world. But there was in Oxfordshire the headquarters of UKAEA, the Atomic Energy Authority. So there was the Harwell campus and the Culham campus within a few miles of one another, where an awful lot of the nuclear activity, work on radioactive materials, on fission power and so on, was being done. And so when you have a big site with appropriate engineering skills and the understanding of how to do these complex projects, it was a natural place to try and encourage the European investment into the Joint European Torus, which is the big machine that's on the site, and then to persuade the UK government to continue to fund with, like you mentioned, the mast upgrade project. That's again a medium scale engineering project. Yes, it wasn't by design. It's by taking advantage of the skill set that's there locally and saying we can build internationally leading projects on this bit of land that happens to have these skills around it.
And maybe one thing to point out now is that the UK Atomic Energy Authority concentrates now, it's just purely on fusion energy. That's the authority's mission now. Ross and Gianluca, again, very briefly, in what ways do Tokamak Energy and First Light Fusion benefit from having other fusion organisations as neighbours? Do you talk to each other? Are you competitors, or are you collaborators, friends or foes?
I think whilst we're both developing very different approaches to achieve the ultimate goal, which is commercial fusion, I think we benefit, and certainly from Tokamak Energy's perspective, we benefit from having other fusion companies like First Light in the same area. I mean, whilst we are competitors, I think we do interact quite a lot. Gianluca and I think this is the second time we've spoken this week. And I think having that competition is healthy. Being in the same area it means that there are certain things where there are common challenges and problems that we can work together. So, I think it is a real benefit to all of the organisations to have, this cluster of fusion businesses in the Oxfordshire area.
John, look at
I want to bring two. I completely agree with Ross. I want to bring two, tangible examples. One is fictional. I think we are still at the stage where the Highlanders are better to group together. It's a bit too early to fight each other, really. And I also think there will not be, unlike the movie, there won't be only one at the end. I think that there is scope for different technologies, potentially for different deployments and so on. That's the first point, very briefly. On the word we're looking for now is cluster, right? So on the benefit of cluster, I have lived my previous career, the benefits of a cluster in my previous career. I was in Formula One for 15 years, and Oxfordshire is, as many people know, is F1 Valley. And there's a reason why when you reach a certain critical mass, there is benefit in, there's the supply chain, the contractors that know the business and they can help you more. So it's extremely valuable. And Oxfordshire now is also Fusion Valley because it is the biggest cluster in the world, right? There are three private companies plus a national laboratory is very important.
Lindsay, we hear a lot from the government in the UK about levelling up. Does attracting, more investment into fusion in Oxfordshire, does it bring benefits to other parts of the country?
Yeah, I think it will do. The intention, so I run the Fusion Industry Programme, which is in its pilot year this year to go for it, is to support the whole of the UK to be involved from the private sector into the public sector to bring us into this delivery era. We've all been explaining how fusion has been in this experimental phase and it's now progressing quite rapidly into the delivery era. And for that to happen, you're going to need a broader supply chain. You're going to need aligned sectors. You're going to need to bring in technology transfers from other industries, other capabilities, other know-how. And whilst we're explaining that cluster is happening for fusion, the fusion technology specific things in Oxfordshire, we need the breadth of capabilities across the UK to feed into that. So it will broaden out. And as we progress, with more examples like we have with Tokamak Energy and First Light Fusion, other companies that come on and those that support into that, this will grow across the whole of the UK. There's going to be benefits if you think of employment mobility. You might start off with a career down in Oxfordshire, but you could go elsewhere or vice versa. It's only going to grow, I think, from here. It will always be supported, as we say, as Chris explained, from that historical perspective. There will always be a heart to home for it here, but it is going to reach further.
Yeah, I mean, this is sort of hugely inspiring, Chris, isn't it? And hopefully there are young people who are watching who've been inspired by this discussion. What opportunities are there for them to work in fusion energy?
Well, just at the moment, the fusion cluster, the community in Oxfordshire, is sucking talent in from all over the UK and all over the world because there are jobs being created. The government's invested a substantial amount of money in the program called STEP, a spherical Tokamak for energy production. And that's created a lot of jobs, not just in Oxfordshire, there are, as Lindsay said, around in the rest of the country as well. But there are more jobs than there are red hot fusion engineers, if you like to fill them. I think that my colleagues at UKAEA would say. The other thing I would point out is that what we need is not all clever physicists. We need an awful lot of really high-level technicians, people who can design and build and operate very complex instrumentation. And these aren't scientists; these are technical roles. And it's so having in Oxfordshire the Advanced Skills Academy, which is an apprentice training school, which is on the UKAEA campus, is great because I mean, I run a lab, and in my lab, having technicians, they are not the bottom of the food chain, they're the top of the food chain, they're the people that make things work. and we need to train them. We need them just as much as we need the PhDs. And so Oxfordshire has those opportunities where people can say, I'd like to become one of these highly skilled technicians, and they can go through the training in the Advanced Skills Academy and really help to build the fusion future.
So Ross, what about other jobs? You know, do we need lots of computer engineers, for example, or, you know, who else do we need?
I mean, it's a really good question. I mean, we've talked a lot about sort of the scientists, the technicians, and the engineers, and they're obviously critical to delivering fusion. And you know, for us, engineers working in magnet technology is very important. And Oxfordshire happens also to be a centre of excellence for superconducting magnets. So you know, we've got the double benefit there of the fusion cluster and the magnet cluster. But you know, in addition to the scientists, technicians, and the engineers, we also need, you know, we need people working in fusion who have experience in project delivery, in you know, building and deploying, you know, commercial power plants. We need, you know, we need commercial people who can help structure the deals. We need finance people who can help raise the investment. You know, we need people working in marketing, communications, and PR who can help spread the message about fusion and how beneficial it will be. So, you know, we need to recruit people from all sorts of different backgrounds and experiences.
Now, Lindsay, I talked about young people, but you've been thinking more broadly, haven't you?
Yeah, absolutely. Within the Fusion Industry Programme, there's an education scheme, and then part of that, we're looking at the skills gaps, as we've just described, what's going to be needed, and how we can support industry to bring that into fusion. Because we need all those good people to understand that there are opportunities for them in a future fusion industry. So we've been considering different ways to support that. For example, returnships, where people, or if people have had different career breaks for different reasons, how we can reach out to underrepresented groups of personnel, and just trying to think through what that could look like. And I think especially with the pandemic, people will have faced redundancies. They'll have this excellent skill set where they've had it in other sectors. They could bring their knowledge into fusion that way. So we're really trying to understand where we could pull in those excellent people from across all of those different skills, and support industry to find them and then to bring them in.
Thank you, Lindsay. So we are almost out of time. In fact, we've overrun slightly by 2 minutes. I can see, thank you everyone for sending in your questions. I can see that Gianluca is answering a question at the moment privately to one of our for one of our audience members. But given that we've kind of come to the end of our time, I'll give you all 10 seconds each to tell to tell people where they can go to for more information. You know, maybe your company website or the program that you work on. Let's start with you, Ross. Where should our audience go?
Yeah, no, I would recommend people to look at our website, tokamakenergy.co.uk, to find out about our technology, our progress, and the opportunities that we offer. Okay, fantastic. Lindsay.
Oh, and me. Yeah, so we have the CCFE website. We also have the @UKAEA official on all of the social media, as well as if you put in UKAEA and search, you'll be able to find us that way.
Great, and the YouTube channel is particularly good, isn't it? Gianluca, where should people find information about First Light Fusion? What's your website?
Yeah, our website, I just put it in a chat too, is firstlightfusion.com, and follow us on Twitter at FLFusion, and obviously you can look us up on LinkedIn. We look we're always looking for people, and we're really pushing to try and fight the diversity issue that everybody has in physics and in engineering. So please do get in touch with us.
Fantastic, thanks. And Chris, from a materials side, where should people be looking for more info?
I mean, these companies need people with material skills. So the same places, UKAEA is hiring all my research group, or at least trying to. So if that's an area that interests you, then the places that are going to need you are the companies and the institutions who are going to design and build these machines.
Very quickly, M in the question and answers asks, are there apprenticeships for young people available in Oxfordshire at the moment? Chris, 2-word answer.
Universities don't deal in apprenticeships very much, but
maybe Lindsay can jump in then.
Yes.
Yeah, you mentioned the OAS earlier, so that's the best place to go and look for that.
Great, that's Oxfordshire Advanced Skills. Thank you. Right, thank you to our panellists. Dane has arrived, he's about to kick me off. So just one final word. If you've enjoyed this discussion and want to hear more on fusion, check out 3 other events at IF Oxford. On Sunday, the 17th of October, you can hear how art is being inspired by fusion science and engineering. On the 21st of October, race through this, you can hear about the past, present and future of fusion energy in Oxfordshire. And if you're fed up watching events on screen, then get over to Blackbird Leys Community Centre for Blast for a hands-on interactive session, all to do with fusion and much, much more. Thank you so much for being with us. Thank you to all our panellists. Thank you to everyone at home. Dane, where can we find information on tickets and how to book them?
There's loads of opportunities. You're absolutely right, Valerie. Thanks. The festival website is if-oxford.com, and we're really happy to have a load of fusion events. And there's a really beautiful sculpture that has been commissioned as part of this Art of Fusion activity. So do have a look at that. Thanks again for all the panelists. A really good discussion about this new innovative and world-leading technology that's being developed in Oxfordshire. It's really exciting to be so close to this hotbed of innovation, and we'll see everybody at future events. Thanks everyone. Bye-bye.
Thank you.